We can also talk about weak bases. We know strong bases, like strong acids, completely dissociate and make their hydroxide. However, weak bases, as we'll see, here is our generic weak base, B, will combine with water, producing OH- and BH+. So the base will abstract a proton from water, producing hydroxide as well as the conjugate acid. And we're going to see that if we do Kc for this, we're going to end up with hydroxide, BH+, and then B. Sometimes you'll see B as negative, and BH would therefore be neutral, but it doesn't really matter. These are just kind of arbitrary. And so we can see that this is very much similar to our Ka, and we'll call it Kb. This is the base dissociation constant. Although it's not necessarily dissociation that's happening, we'll still just call it that. So it's the base constant, essentially. It's the same thing as Ka, except in terms of base. And notice that we have now, instead, we have hydroxide concentration. And with hydroxide, we'll be able to calculate the H+ or POH and pH accordingly. So this is the same as Ka, except it's for bases. In Discord, in your extra resources tab, I have put another table of common bases. And you use Kb exactly as you would for Ka, except you're calculating POH instead. You can calculate the pH, of course, because we remember that POH plus pH is 14. We can do the same thing. It's important to know that the Kb equation, this expression, is always for the conjugate acid of B, so BH+, as well as your original base. And this time again we have that hydroxide term. So if you excuse me, want to take a look at this in terms of an actual equation, why don't we use ammonia? Pretty common one. So ammonia plus water turns into hydroxide plus the ammonium ion. So B plus H2O, hydroxide BH+. So B is NH3, BH+, therefore is NH4+. And so we're going to see that Kb for this solution, or rather for ammonia, is actually the same as it is for acetic acid, right? Remember, acetic acid has a Ka of 1.8 times 10 to the negative 5. Interesting enough, ammonia's Kb is the opposite, or it's the same number, but it's Kb. Let's actually move this aside. Well, we'll deal with that later. Let's say we have 0.125 molar ammonia. You know what? No, let's do a different number. How about 0.5 molar? Yeah. What's the pH of that? Well, just like before, we're going to do an ice table. So we're going to start with 0.50. We don't have to put anything for water because water's a liquid. Liquids don't matter for ice tables. The reason is because concentrations of liquids and solids don't change. If you're adding more water, you're now expanding the volume of that water. And so your mole to volume ratio is always for water. It's 55.5, but it's always the same. So we don't have to ever include solids or liquids. All right, so if we take a look at our OH, that's 0, and our ammonium is 0. So we will subtract x, add x, add x, 0.50 minus x, x. Same idea here. We have our Kb, so we know that x squared over 0.50 minus x will be equal to our Kb. Let's go ahead and make our assumption that x is going to be smaller than 5%. We will always check. And in doing this, if we solve for x using our calculator, 0.5 times 1.8 times 10 to the negative 5th square rooted, we get 0.003. And we're going to need one more sig fig. So we can see here that we're going to want to go ahead and do our check. 0.003 divided by 0.5. We get that it's 0.6%. Same as our percent ionization, by the way. So we have 0.6%. We're good. Assumption is valid. Our assumption gets a happy face. So 0.6%. We're fine. We can use this X value then. So that's our hydroxide this time. So it's not H+, it's hydroxide. Meaning, this time we can find the POH. If you want, of course, you can find H+ from OH- directly. I just typically find it easier to use the P's because I don't like having to deal with all the crazy exponents. But you can solve for H+ and then go to pH from there, from this OH concentration. But I'll do it from POH. Okay, if we go ahead and log this, negative log 0.003, we get, oops, wow, 2.52287, whatever. We have 2 sig figs here. Remember that pH is 14 with 3 sig figs minus POH. 14 minus 2.52287, which is equal to 14 minus our answer is going to be 11.47. Actually, we'll make it 4.8. We have to round. All right, so with our 2 sig figs, we're going to have our pH here. So as we would expect, since this was a weak base, our pH should be above 7. We have a basic solution. All right? And so we're going to see that for bases, it's much the same thing. There is a table of common KBs for you in Discord.